All right, now we know the general balance equation and we've seen an example. Let's talk about how we do balances and how we make our lives easy. I told you that there's only one equation that you need to learn for the entire semester, and I want to kind of convince you of that in this video. So, first things first, two different types of balances can technically be written when we talk about balances. So, we can have what's called a differential balance. And this indicates what's happening at an instant in time. So each term of the balanced equation is a rate, and it's usually applied to a continuous problem or a continuous process, excuse me. So it's like a derivative, right? We're looking at a point in time. So we'll be using things like m dot, n dot going forward. And this is pretty much this is the common way that we do this in the class, but it doesn't mean that we can't look at other things as well. The other version is an integral balance. And an integral balance looks at what happens between two instances in time. Each term is an amount of the balanced quantity, excuse me. So that's m and that's n. Realize that there's no dots on those. And we usually apply this to a batch process. So you can think of this as an integral. If you remember from calculus, an integral is the area under the curve. So if we're looking at two instances in time, A and B, we need to look at the area underneath the curve. So it can be positive in points, it can be negative in points, right? And so this is normally used when we're looking at batch processes, and differential is normally used when we're looking at instance in time. So we're using things like quantity per unit time. So just two types of balances to be aware of. When we solve them, we don't really use a lot of the calculus notation. So remember that m dot, let's push up a little bit so we can see on the page. Remember that m dot is the same as dm dt, right? And so we'd be doing integrals over here, but we tend to use just different notation because it's just a little bit easier to solve mass balances. If you're really interested in learning the calculus behind it, happy to teach you it, but I think it's a little bit easier to just try and simplify. So, integral and differential types of balances. Let's talk about how are we going to simplify a mass balance. So if we have our mass balance equation, right, we have input minus output plus generation minus consumption equals accumulation. And I just switch some of the terms around. As long as my signs are the same, it doesn't really matter. There's lots of different problems that we're going to encounter. And it would be really, really nice if some of these terms were zero, because it would make our lives a lot easier. So we have some rules that we can use to try and simplify this mass balance so that we don't always have 5 different terms in the system. So if we're balancing total mass in a system, let's write out this mass balance equation again. I'm going to use the letters to abbreviate and save some space. You can write out the words if it helps you. If you're balancing total mass, we know you cannot create or destroy mass. That means there can be no generation and no consumption of mass, which means that our generation term is going to equal 0 and our consumption term is going to equal 0. And throughout the semester, I try and use a little 0 with a line through it, so it's different from my O to hopefully help you out there. So in this particular equation down here, we can cancel out the G, we can cancel out the C, and our mass balance is going to simplify to input minus output equals accumulation. So whenever we start a problem, first thing you want to do is, are we balancing total mass? If we balance total mass, you can't consume or generate any mass. You can get rid of those two terms and make your life a lot easier. Next, if the balanced substance is non-reactive species, let's write our mass balance out again. Always good practice to just write this out every time you start a problem. If it's a non-reactive species, you're not going to generate or consume anything in the system. So same thing as the last time, generation can be set to 0 and consumption can be set to 0. So this balance, again, will simplify to input minus output equals accumulation. Anytime you can get rid of terms, that's going to help you quite a bit. If the system is in steady state, I have my equation written out. If it's in steady state, this means that it's not changing with respect to time, which means that we are not accumulating anything in our system. So we can set accumulation equal to 0. So if we set accumulation equal to 0, one thing that's nice to do here is to move these negative terms over to the other side of the equation. So we'll get input plus generation equals output plus consumption. And that's just an easier balance to do for us overall, right? So those are some general rules to help you try to make your life a little bit easier when it comes to mass balances and trying to simplify out. Let's talk just a little bit more about that because this is really critical. If accumulation equals 0, which is what we just did, we know that input plus generation is going to be output plus consumption. And if the balance is non-reactive or it's on total mass, many times input is just going to equal output, no accumulation, right? So if it's non-reactive and it's continuous and it's steady state, right? So steady state means accumulation equals 0. Continuous, right? That doesn't necessarily tell us anything about this, but if we have non-reactive species, that means no generation or consumption. It's on total mass. So if it's a steady state process, no accumulation term here. So equals 0. There we go. That makes it a little bit more intuitive. So why is this the case, right? Why can we do this, all right? So, right, we have the law of conservation of mass. And we've talked about this before, right? But for any system that's close to the transfer of matter and energy, the mass of the system must remain constant over time. The system's mass can't change, right? So you can't add or remove any quantities. So this is really important, right? The fact that we have this very basic law. So the quantity of mass is conserved over time. Many times if it's, well, all the time actually, if it's continuous and steady state, you're always going to get input equals output. We also have the law of conservation of energy, right? So the total energy of an isolated system has to remain constant. It has to be conserved over time. So this is going to play into our balances later on. Our first set of balances throughout the semester are going to be mass balances, but this same general balance equation that we've been writing also applies to energy. So that's going to be important later on, is the same concept of mass also applies to energy. So just remember that steady state and continuous means that the values don't change with time. Last thing to kind of finish up on this particular lecture is balances on batch processes. So by definition, for these batch processes, accumulation is going to be final output minus the initial input. And accumulation can also be generation minus consumption. So we get this balance of input plus generation equals final output plus consumption. And we only make a small difference but here with this final and the initial because it's a batch system. So you can have many batches coming in, so many rounds of doing an input, and then you're going to have a final output. And we only want the final thing that comes out of the system. So that's how we can potentially make our lives a little bit easier to solve these types of problems going forward. So when you read problem statements, think about, is accumulation 0? Is input 0? Is output 0? It's going to make your life a lot easier solving these problems.